All right, we'll go ahead and get started. Good morning, everyone, and welcome to our very first webinar in our new partner webinar series. I'm Autumn Phillips. I'm an R&D chemist here at Inorganic Ventures, and I'll be moderating today's session. Joining me is Dr. Sergei Leikin from Texas Scientific Products, who will be giving a presentation on troubleshooting the most common problems on ICP-OES and ICP-MS spec. Before we get started, I'm just going to go through a few housekeeping items. So at the bottom of your screen, you'll find a Q&A box, and there's also a chat feature there. Please submit any questions through the Q&A box just so we can go through those a little bit more smoothly at the end and check those off and make sure we get everything answered. This presentation is being recorded. So after today's session, you'll be able to go into our website under the technical videos section and view this recording if you want to go back or if you're not able to join for the entire session. Also, if you or someone you know is looking for some more in-depth ICP training, we have a new on-demand learning platform called Ivy Ignite. So you can check that out through our website. And we'll also be taking our ICP conference on the road for the very first time this December. So if you want to, you can join us in Indianapolis, Indiana on December 4th and 5th, or in Columbus, Ohio on December 6th and 7th for our very first traveling ICP conference. So over the course of 2 days, you'll be immersed in all things ICP testing, including learning how to optimize your instrument, improve sample prep and analysis, and how to choose the correct method. Visit our website or feel free to reach out to us after this presentation to get more information on that. And we'll also have some QR codes available on the final slides if you want to visit the website through those. So joining us this morning to give this presentation is Dr. Sergei Leikin. Dr. Leikin is a co-founder and managing director of Texas Scientific Products, a supplier of high-quality consumables and innovative sample introduction systems for ICP atomic emission and mass spectrometers. Prior to starting at TSP, he worked as an applications laboratory manager for premier instrument manufacturers of both ICP-OES and ICP-MS, as well as microwave digestion equipment. An analytical chemist with an extensive scientific background, Sergei utilizes his 36 years of experience in atomic spectroscopy to help solve everyday real-world material analysis problems. At TSP, Dr. Leikin directs the new product and business development while keeping the focus on what he likes the most, problem solving. Sergei received a master's degree in optical electronic systems and a PhD in analytical chemistry. We're very glad to have Sergei with us this morning, so I'll go ahead and turn it over to Sergei.
All right, thank you. Thank you very much, Autumn, and thank you everybody for joining us together. I also want to thank the team at IV for inviting me over, giving me opportunity to share my experience with you today. We're going to be focusing, the format of the webinar is to go through the very common ICP-MS problems that any analyst experience on the daily basis or weekly basis. And then we'll leave hopefully about a few minutes, 10 minutes for questions and answer section. So what the typical problems are? The sensitivity loss or precision. The sensitivity can be okay, but precision suffers. And we run the calibration, and the first QC did not pass. Let's dig into that and see what can be done, how to address it in the simple way. So when we run to something like that, so here is typical action plan. We're trying to clean something, we clean the torch, then we clean all the glassware, then we replace the pump tubing, then replace all the tubing, then we replace the torch, and replace all the glassware. And I'm sure every one of us have such an experience. And then at the end, it's frustrating, but nothing gets fixed. So where the 90% of the problems coming from? I'm not going to give you a secret. This is from the sample introduction. And actually, if you look back at the action plan, so it was pretty good hint to start with that type of components to look at. But let's try to focus on getting like what's actually going on, where we not just do by trial and errors, but more focused on step-by-step things. Torch alignment. It's a basic thing, and a lot of instruments, actually all of them, have some type of a routine to align the torch. Torch injector ID. Sometimes the injector ID can change because you order the wrong part number, or your supplier may made a mistake and put a torch with a different ID. That will affect the sensitivity. And there are typical problems everyone went through is blocking the nebulizer, or in some extreme cases where you run difficult samples, it can even block the injector of the torch. So torch alignment. It's a good idea not to just rely upon the routine that any ICP manufacturers have on their instrument, but actually physically check to make sure it's centered and the torch is right in the center of the coil. The reason for that is it may be beyond your control. Sometimes the power goes off, and when you turn the instrument back on, the stepper motor moves your torch box, and goods end up in the same spot, but it may not. So it's a good idea always to physically check. Using this routine is also should be done only when it's really needed, not on a daily basis, because you're introducing the variable. When you replace your torch or remove it for cleaning and put it back on, yeah, that's where it should be applied. And the other practical advice I'd like to give you is to keep the records of the intensities that you're getting out of your optimization solution or tuning solution, which typically it's a manganese, and you monitor manganese 257 line, both in radial and axial mode. On ICP-MS, it's a different tuning routine. It's more complicated, involved more of the parameters. Another part where it's actually important, especially when you put torch in and out, although the instruments now, the design of it kind of fixes the torch position. But I specifically brought it up here just to show you so you can look at, because something can happen, and what you need to look for is whether you have a gap between the injector and the first loop of the coil, like it's showing on the left picture. And if you have something like that, which is the torch is elevated, you see it here, and there is no gap, so that definitely needs to be fixed, and your sensitivity going to be affected. So the other way to look very brief and quick way to look at your sensitivity loss is just to simply look at the mist in your spray chamber. And you see here on the picture, it's better be seen when you have a piece of black paper behind the panel on your or attached to the panel of your instrument. And here is so you see the mist here. It's a bit of a brief video clip that shows it. And so if we'll see if the technology will copyright and get our video going. So then we'll just move to the next slide here. We'll try to repeat it. So looking at the mist, if you need to, you can pull out the nebulizer right from your spray chamber and just hold it in your hands and just observe the mist. It should be solid. You should not see any large particulates, and it should be stable. So that will give you some idea of what's going on with your nebulizer. So here is the more of a practical example from the real life when the nebulizer get pulled out from the instrument. And actually, you don't need to run the plasma when you do that. So you can actually just apply the nebulizer gas flow and hold the nebulizer in your hands, like on this slide. on this video, and you can actually see this the whether you have a mist or quality of the mist and where it's going. The reason behind that, it was a bit of a mystery that we have to solve on site, where the nebulizer produced the mist, but when inserted into the spray chamber, the signal was lost. So we have to look, and what's happened is there is an adapter here. An adapter has a collar at the end. When the nebulizer was pushed all the way into the adapter, so it just blocked the sample orifice, and the signal was lost. So that was an interesting mystery that we have to resolve. Another reason for sensitivity loss is the blockages of the nebulizer. And it happens, quite often if you have concentric type nebulizer, they are known to be prone to clogging. Here you can see a different type of blockages. It can be either on the sample channel or on the gas channel. And on the right picture, you can see the actual micro picture of the tip of the actual nebulizer with the sample deposit. So it is important to separate when the nebulizer is blocked. So it can be blocked for two main reasons. And the first type of blockages is it can happen right on the sample channel. To look at this, you're looking at the mist, and the indication of it is mist is inconsistent, or it can be skewed to one direction. It can be a large particle present in the mist. You can see it when you look at this. You can see actually the large particles. If you don't see any particles, that means your mist is good. And in the more extreme cases, when the sample channel is blocked completely, so that your pump is trying to push the sample through the nebulizer, and the back pressure creates on the pump tubing, and your pump tubing will pop off, disconnect at the joint where your sample line is connected to the peristaltic pump tubing. The other type of blockages is on the gas channel, and these can be diagnosed also relatively easily. Modern instrumentation monitors what we call back pressure, or pressure that apply to the nebulizer. It's a good idea to keep track of it. If you get a brand new nebulizer that works well, and you apply, look at the flow that is applied in your method, and just record the pressure. So if the pressure goes up with the time, so then your nebulizer is partially clogged. If the pressure is down, then you need to look for the leak somewhere in the sample reduction system. So this is probably in my view, one of the most effective diagnostic tools that you can use in your practice. It's called we call it the yttrium bullet test. Why yttrium? You need about 5,000 to 10,000 ppm of the solution. It just brings the colors, and the colors are very visible. You can actually easily see that. And the bullet is shown by the arrows. It's the area between the blue zone, which is the emission zone, and red zone, excitation zone. So this position of the bullet is defined by each instrument manufacturer, and that we should be following to get the proper optimized sensitivity as a quick thing to do. And looking at the position of the bullet relatively to the coil and the torch. When you've done it for a while, you can actually judge by the intensity of the colors, and you can immediately notice the colors are not as bright, so you're probably something wrong with the nebulizer. And this is actually the diagnostic tool that's used by the ICP manufacturers when they go quickly on site, and we supply it to some of the manufacturers as in the sample reduction kit. And the other parameter they can look at is the bullet stability. So if it bouncing around, then there is something to check on. So here is another option to look at the bullet. So this is when you run organics. This is how the plasma look like. And you see this green color coming from the carbon. On the left picture, you see the bullet is kind of hiding behind the loop of the coil. And on the right picture, it's showing where was a proper position of the bullet. Now we're looking and moving to the next main common problem, which is precision, degradation of the precision. So of course it can be done, can come from the nebulizer blockages. It can come from contaminated spray chamber. Your tubing may be worn or over tightened, or the injector of the torch is in a bad shape. So quick and practical way to look at this is to look at how your spraying chamber is drained. And this is the picture of the pump tubing that has this nice steady segments of liquid followed by the segments of air. So if you see longer segments of liquid, that the spray chamber is probably not drained properly. Yeah, this is a very quick thing that you can diagnose yourself. So here is the how the spray chamber look like if it's contaminated. You see what we call the beading formation or large droplet formation on the top of the spray chamber. And the way to address it is soaking in any lab detergent. So it may be some of the organic content there. So it's like cleaning your dirty dishes. So similar approach. So this is, this is what I did myself. So just forgot to release the tension on the pump overnight and come in the morning and try to fire it up, and then see that the tubing is flattened. So this is definitely should be replaced immediately. And plus, additional, as I mentioned, the way you tighten the clamp on the pump. So even if the tubing is good, and also should be stretchable, that's another parameter. So even if with a good tubing, but the clamp is over tightened, so your precision may also suffer. The one other thing to look for is the injector. It's the way it looks, because this is the most critical part of your torch. And here's the example of the fixed torch. There are demountable torches, and here's the quartz one. And a lot of you are using the ceramic injectors, but still, even ceramic injectors with the time, so they're gonna get worn. So the torch itself, and this question comes very often. Well, my torch is discolored, and can I use it, or what is going to affect performance? So the outer shield of the torch, it can have very not nice looking colors, and it may be even partially devitrified, but you still will get a decent performance out of this torch. But if your injector is worn like that, this is definitely an area of concern, or replacement of the injector or the torch. So quite often the injector is being worn because the some of the plasma running parameters of your sample, the samples, we're not just running drinking waters, right? So there are some very tough samples that every one of us have to run. So the way to minimize this process is to, as shown on the by arrow, is to increase the auxiliary flow or intermediate flow, using different terminology, so that will lift the plasma up away from the injector, and so all these processes of corrosion is going to get delayed. So you extend the lifetime of the injector. And now moving to the last point of the common problems in this presentation. I'm sure there are many. So your QC did not pass. So what the first thing to look for, and there is a number of reasons. So we get the good calibration curves, and this is an example showing up here, and we get very excited, everything looks great. But what is really important is to look at this data. which is the different softwares, different manufacturers, they have it in some form. It's a relative difference in percentage between your what you put in your what is in your standard calibration standard and what is actually reading by the instrument. If you have somewhere like here, it's a pretty good example, everything within maximum below 3%. But if one of the points is closer to 8 or 10%, then and this point is used as a calibration verification, then you're right on the border, and it's very easy for the instrument to not pass a QC, fail it, because it's a high percentage. But it's actually nothing wrong with your instrument, because it's going to read exactly what the calibration data says it to read, and you have to look further to address it. And to summarize it, so I've tried to give you in this limited time the tools that you can use on a daily basis when you run to some of these common problems, which is the torch alignment or torch monitoring when the torch is moved, monitoring the intensities of your tuning solution. Observing the mist. You'll see a lot of things can be done just by simply looking at the mist before you do the calibration, because after you've done it, you lost all this valuable time and run to a problem. Using the monitoring the back pressure, it's a health of your nebulizer, and utilizing the bullet test to diagnose your instrument. I want to thank you for your attention. Thank you, because I've seen people sign up from all over the world. I'm sure it's pretty early on your end, and I pass it to Autumn. Thank you for questions.
Awesome. Thank you, Sergei. That was a great presentation. I'm just going to start going through the Q&A so we can get some of these questions answered. So the first question, Sergei, is, I'm extremely new to ICP. What is the difference between ICP mass spec and ICP-OES, and when is one preferred over the other?
Yeah, the ICP optical emission, ICP mass spec, in my view, are complementary techniques. And the separation between them is, so the common thing is the source. Both have ICP, inductively coupled plasma. And ICP-OES, as we call it, is emission instrument, optical emission, and MS is mass spectrometry. Mass spec is generally more sensitive than ICP emission, probably in the order of 1,000 times. So to choose between them, it really depends, but typically if you're looking for extremely low detection limits, this is where you go to mass spec, and when you get some tough samples and using ICP emission. But there are some exceptions, and actually we were showing it at one of our applications that recently done, actually in collaboration together with Autumn, where we use ICP-OES to do typical mass spec application, which is analysis of toxic elements in cannabis, just using proper sample production, more effective nebulizer, and doing some tuning. Actually, the work been done in collaboration also with CM folks, and so they've been presented.
Yeah, and so we actually have a paper it's mentioned in one of the later slides here that you'll be provided with after this session. I think it's not that one, maybe the last one. But it's an article that's coming out in Spectroscopy in the October issue about how to lower your detection limits for ICP-OES applications. So definitely check that out if you are using an OES and you're trying to do a trace analysis. So the next question is, will the sodium bullet test work as well as the yttrium bullet test?
Very good question, and I mentioned, and I remember to mention it, absolutely. So any bullet, anything that you can run that makes this area that I showed visible, yes, sodium is one of those that doesn't require to get yttrium or anything else. Yes.
Okay. All right. And then the next question, how often should pump tubing be changed?
Yeah, that's I would refer you to the, there is I skip this point because there is a very good comprehensive advices from your instrument manufacturer. There is a maintenance schedule should follow, but generally speaking, if there are two types of tubing. One is where the sample goes. This is way more critical. So if you're running 8 hours a day at least, so that should be changed at least once every couple of days. And again, look at the health or state of your tubing physically. So if it should have any flattened spots, and it should be stretchable. If those two things present there, you can put the tubing and back on the instrument.
Right. Yeah. And I would also say if you are going to use it for multiple days rather than changing it each day, just make sure that you unclamp it as well, so it's not being stretched over the pump all night while it's not even being ran.
Yes, absolutely. That's actually very often getting forgotten.
Yeah.
That's what the example I showed on the presentation.
All right, and the next question, if precision is only an issue with specific metals, for example, aluminum, do you have any recommendations besides making a tighter calibration curve for that given metal?
Well, the precision does not necessarily correspond to the tightness of the curve or what I mentioned. It's actually more of an accuracy issue than the precision. Precision is the consistency of your results or low value of your RSD or relative standard deviations. So I'm not quite sure how to answer this question because, yeah, that's a bit of a, now, if it's aluminum as an element, aluminum as a matrix, but if that relates to the precision, not accuracy, then it's maybe have to look at how much sample go into the plasma. Maybe the power needs to be brought up to compensate for the load. So things like that.
Yeah, I would also say just make sure that you have your peak centered properly and your background points are set correctly. You may need to go in and look at the spectra itself to see like what your background is doing, because you may need to do like a single side background point if you have an interference on one side or the other.
Yeah, that's a very good point. Yeah, I didn't put it in my presentation because it's more from method development thing rather than the what we are focused on today. But yeah, Autumn is absolutely correct. So the peaks can be shifted with the time. And one other thing could be a reason for poor precision is your peak shifted and you're not measuring on peak anymore.
Right.
So, but in this case, yeah, I think the tuning solutions are recommended by the manufacturers that should be run maybe depends on the instruments every couple of weeks or 3 weeks or whatever.
All right. So I work with a fairly saline matrix geothermal fluid. We use ceramic accessories due to the characteristics of the sample. How could we evaluate the low precision in the mist chamber and the rest of the accessories? So you could, yeah, I think she's just asking because they don't have a glass spray chamber.
I see. Yeah. So yeah, if yeah, the yeah, that should have been pointed out. So the evaluation of the mist is it can be done when you have a glass or quartz spray chamber. So when you have something like from Teflon or non-transparent material, so then yeah, obviously you can't do it. The same thing also, you cannot see the bullet if you run the ceramic torch. That's in my view one of the drawbacks of the ceramic outer shields that's been out on the marketplace. Because it's like seeing the plasma will tell a lot many of the times, and then you're working blind with the ceramic torch. But in this case, yeah, you can actually, it's not maybe completely safe, but yeah, pull in the nebulizer and see how it runs with your matrix and just turn it away from you. So this is the only way you can actually look at the mist. But when you have high salt matrix, so most of the problems and what should be used is any nebulizer can salt up, even the one that's non-concentric and more robust and everything on the gas channel. And to prevent this, the argon humidifier, not prevent, but to slow down this process dramatically, argon humidifier should be used along with your nebulizer.
All right. And then this is somewhat similar. What is the best method to check the health of a spray chamber that is not glass and cannot be looked through to check for droplet formation?
Yeah, that's well, get a transparent spray chamber. that's the best way to. But seriously, well, there are some actually transparent PFA spray chambers on the marketplace. But seriously, yeah, if you don't need to swap. So the only way is to take it apart, because these Teflon spray chambers, they're demountable. So you can actually take it apart and take a look where you see the bead formation or not. But regardless of that, I think the practical thing is, if the spray chamber is made of Teflon or any type of material, it has the special coating that the manufacturers do to facilitate the drainage, because the Teflon is not wettable material, and the beading on it is a natural thing. So the coating is going to wear out. And you have probably, if you run every day, probably depends on between a year or maybe two of a lifetime. Some manufacturers order recoating, but that's a long process, and that's one of the things. But if you run into this problem, it's either to try to refurbish it or to get a new spray chamber. Unfortunately, yeah, that's the thing.
Yeah, to help with droplet formation, you could also soak your spray chamber. If you're seeing poor precision or degradation of your signal, you could try soaking that in a surfactant solution. So we use RBS 25 at 25%, and we just soak the spray chamber for a little bit and then wash it off, obviously, really thoroughly with water. But that can help recondition the surface of your spray chamber so that those droplets can't form as easily, and you'll get a better mist from that too. So next question, is adjusting the tubing flow more of an eye test?
Yes.
More of an eye test, or is there a correct how-to guide for knowing you're getting correct flow from pump tubing?
Yeah, there are some device. I mean, it depends on what you're looking for. So if you put the tubing, the correct flow is defined by the tubing internal diameter, which corresponds to the color code on the pump tubing. For example, orange is 0.89 millimeters ID. Black is 0.76. So but to check on the tension of the tubing, so the proper way to do it is just to eyeball it and look at the beginning. So you look at the air bubble, introduce the air bubble, and then yeah, it's just sun coming out in my office, just trying to escape from the sun. But so look at the air bubble. You introduce it by pulling your SIPA tube, and then you release the tension up to the point where the bubble stops. And then after this general cremation, about 3/4 to 1 turn more, and you will see again, you check the steadiness of this air bubble that you introduce manually going through the pump tubing. That's the way to do it.
Okay. All right, next question. What causes should we look for if the internal standards fail?
Yeah, that's another good question. Yeah, the one of the practical thing is to use internal standard in general in your methodology, and then if the precision can degrade for the simple reason that I showed, but in more complicated cases, it may be element or analyte related. So if your internal standard is run and you see good precision on internal standard, but something happening on your analytes, so then the problem is somewhere else. At least your sample introduction is working fine. So if your internal standard precision degrades, then it's definitely need to be looked at where it's happening. And the first thing to check would be, the most common is the T connectors or Y connectors that's being used, so the connection can be loose or worn out or something like that. So this way, when it's teed into the peristaltic pump tubing, so something happening there not consistently. Or the other thing is replace and look at the pump tubing that provides the flow of internal standard in particular, because there are two pump tubing. One provides the sample flow, another one provides the internal standard flow. So the sample pump tubing, which could be, for example, orange and black, could be good health, but you're in the pump tubing that delivers the internal standard solution, which is usually much smaller diameter to minimize the dilution of your sample. It's either orange green or orange blue or whatever. It's very tiny, around 0.2 millimeters plus minus. So if that tubing are worn, then this is where your problem is.
Okay. How can I tell which element wavelength would be best to report from or most consistent?
That's the that's a debatable question. There's no direct answer to that. It also depends on the application. So the general advice I can provide is to use at the beginning, if you're new to the ICP. So first go to manufacturer recommendations or application people on your ICP manufacturer, or reach out to any of us or resources that you got. But then include a few wavelengths that's typically recommended by the software and just look at the performance. Ideally, the performance should be similar, but different lines have different parameters, atomic, ionic, different robustness, and they will provide different results. So typically, atomic lines in ICP, so they can, get you when you have a high loaded sample with matrix, so that maybe give you worse precision than, for example, ionic lines that more robust. So things like that. But yeah, you're choosing a few different lines and then look at the performance and see what does the best.
Yeah, that's actually a really good way to tell, is just to always check multiple wavelengths to make sure that you're not getting some type of an interference on one versus the other. And so on OES, those lines should agree. So the concentration you're getting should agree between lines. And if one of them doesn't, then that's probably an interference or something else going on. So you should use a different line for that. So next question, do you have advice for high TDS samples?
Well, there are many advices for high TDS samples, and that's actually kind of our specialty. But briefly, first, get the right nebulizer. Second, get the high power and have the argon humidifier in line with the sample. So that would be three typical parameters to look for. Mm-hmm. And it depends on how high TDS is, look and adjust the auxiliary flow, like I showed on one of the slides. Generally increase the auxiliary flow up to leave the plasma of the injector.
Okay. The next person says, thank you for the presentation. It was really good. I use ICP-OES for organic samples, and I know there's use for O2 and really high carbon samples. Can you please explain how that affects? Thank you.
Well, when you look at the carbon, there are carbon bands, molecular bands that are being seen in the spectrum. And it depends on the element in certain spectral region where it can affect the results. But doing the correct, selecting the background point and peak point where we see the structural background is one of the way to deal with it. You have to physically see the spectrum, and this is done from during the method development. So the other thing is depends on the volatility of your organic matrix. If it's too volatile, it overload your plasma, and you may run into problem even shutting it down. So in order to deal with that, you can do two things. You can, number one, decrease the nebulizer flow to limit amount of sample, also decrease the speed of your pump, and or put the tubing with a small ID when it's really needs to be cut off to reduce the sample amount going into your spray chamber and the plasma. But rather than that, also, the obviously the calibration on the organic matrix needs to be done based on the similar matrix. Oil analysis are very widely used by thousands of labs, and it's organic matrix. The solvent is used, either kerosene based or similar, and the standards are made in oil. If the oil is being analyzed, dilute with the same solvent with the internal standard, and it's sort of a matrix matching the organic sample that you're on. It's not usually ideally matched, but in this case, it's pretty close because your sample always different than your calibration standard. And the other example, people now are looking at running the actually disposed of oils to rework them and get the biodiesel or things like that. So the raw materials for that is this greasy oil that collected from the things like Burger King's, McDonald's, and everything. So that's a pretty nasty sample. And of course, it's not going to match exactly the standards in oil, but that's a pretty close estimation. And the analysis is actually being done quite well on that.
Okay. All right. So I think we have time for about 2 more questions. And then the other questions we'll try to reach out to you to answer any of those. I know we have a lot left, but we're running up on time. So next question is, you mentioned monitoring our intensities of our tuning solution. We do this, but I've noticed 10 to 20% difference between combinations of spray chambers and nebulizers, all cyclonic spray chambers and concentric nebulizers. Is this concerning? They all seem clean and not blocked.
Yeah, I wouldn't be concerned with 10 to 20% difference, although it sounds a bit, but okay. So 2 different types of cyclonic spray chambers. If we're talking cyclonic, baffled, there is a tube inside the spray chamber, non-baffled. By the design, if you put one versus the other, you get 20% difference in the signal, right? So non-baffled will give you higher signal than the baffled. So baffled is going to filter large particles, and usually recommended for inorganics, but my preference is to use baffled spray chamber because you get a finer mist and you get better RSDs in general. So detection limit gain for baffled versus non-baffled is debatable, because you may have a high RSDs with high signal and the detection limit is going to stay the same, but it's a question of the preference. So the nebulizers, yeah, you can use the same concentric nebulizer, but even, I mean, we manufacture our own nebulizers, non-concentric, that do not clog, but any manufacturer will tell you that there is a variation. There is no way to produce nebulizers within very, very close to each other. It's a production thing. So I would say 20% variation between nebulizer and nebulizer of the same type and style is too much. Usually, but you should expect within plus minus 10%. We actually see plus minus 5, depending on the nebulizer. So, but generally speaking, if you use different type of things and getting one nebulizer versus the other from the different manufacturer, 10%, I don't think it is a concern.
Okay. All right, and then the next question is, I have noticed that Inorganic Ventures indicates to avoid any type of glass in sample preparation for lead. Why is this the case, and how trace can you get before this becomes an issue? I can answer that. So a lot of times the reason that we avoid packaging in glass is just because of the contamination issues. Lead isn't actually a huge concern for glass. So maybe you're thinking of a different analyte. So for glass, the typical concerns are aluminum, barium, obviously boron, calcium, gallium, iron, nickel, potassium, sodium, strontium, zinc, and zirconium. And so any type of trace analysis with any of those elements, we would generally try to package in LDPE, which is the cleanest container material. But yeah, lead shouldn't really be a concern for glass. It is a contaminant in nitric acid. So if you have a higher concentration of nitric acid and you're looking at low-level lead, that could potentially be a concern. So we'd want to use a higher purity nitric acid. But yeah, lead should be fine in glass. All right, well, I'll take one more question. Do you know if there are labs that have been able to test for calcium, sodium, or magnesium with ICP-MS spec?
I cannot name particular labs, but those elements, yeah, they're being tested by mass spec. So the days where, yeah, calcium is, yeah, I don't see any problems with calcium. There is a number of isotopes that can be done. I think question may be more related to the high concentration of those elements rather than to elements by themselves, which mass spec is more geared towards the very, very low levels. But modern instrumentation have all these features where the sample can be diluted online with the gas dilution module and brought up to the concentration that's comfortable for the detector. So yeah, it's either to dilute the sample to get to the comfortable level for mass spec, or to get the dilution online. Yeah, I don't see any problem with that.
All right, and very last one. You shouldn't do the bullet test with ICP-MS spec, right?
Yes, yeah, the bullet test more related to ICP emission. Yeah, if you run, you didn't need to run concentrated solution to mass spec. That's quite a bit, especially if you're using yttrium as the one of the internal standards.
Mm-hmm.
So yeah, that's actually a good question. On ICP-MS, the diagnostics for like the health of the nebulizer and everything can be done offline just by looking at the mist and things like that. So yeah, definitely, yeah, the bullet is. Plus, it's difficult to be seen in ICP-MS as well on some of the instruments.
Yeah, and with that RBS-25 surfactant solution that we were talking about as well, that helps recondition your spray chamber, at least with that particular one, RBS-25, you don't want to run it on a mass spec because the really high sodium content, because that can cause a lot of problems in your instrument.
Yeah, I also used RBS-25 but diluted one. So actually, when I show you the picture of the spray chamber, so that happened to me. So we test our nebulizer. Every nebulizer that we manufacture, that's going through the QC. And then I see we look for two things: for the sensitivity that we try to get within plus minus 10%, and the precision, have to pass 10 measurement less than 1%. Mm-hmm. And then all of a sudden my precision, goes up, and I'm looking at the things, this, that, and then I open the door and see the spray chamber and say, oh my God. But in the middle of the run, so argon goes. So what I did is just to quickly grab the RBS, dilute it to a few percent, and run it through the instrument. So then I immediately see this bright color speaking about sodium bullet running. Yeah, so it's loaded with sodium, and it have to be something you have to be aware of. That's why the recommendation that Autumn mentioned is to soak it and then rinse it with DI water before you put it back on the machine.
Right. All right. Well, I think we're about out of time, and I apologize for not getting to some of these questions, but we'll try to reach out to you all offline to get those answered as well. And thank you everyone for joining us today. We really appreciate your time and attention for this presentation. And please feel free to reach out to us or TSP if you have any additional questions, and we'll see you next time. Thank you.
All right. Thank you. Thank you, everyone.